Today's gate question is, the loop transfer function of a negative feedback system is G of s into h of s is equal to k into s plus 1 by s into s plus 2 into s plus 8. The value of k for which the system is marginally stable is. You'll see the solution. This is the problem from RH criteria. Routh-Hurwitz criteria. Routh-Hurwitz criteria. First, to explain the stability of the given system, it may be marginal, stable or unstable, first we need the characteristic equation. Characteristic equation. What is meant by characteristic equation? 1 plus g of s into h of s is equal to 0. Just do it. Okay, if you multiply all these terms, you are going to get okay. So now this is called characteristic equation. Now with this characteristic equation only we can define the stability of the given feedback system. Let me explain about stability of the system by taking the characteristic equation. Okay, first I'll speak about stable system. For stable system, all the roots of the characteristic equation lie on the left half of the S-plane. Okay, see here, this is the characteristic equation. It has 3 roots because it is having S cube term, it has 3 roots. Now find those 3 roots. Then finding the 3 roots, just you locate those roots in S-plane. What is actually S-plane? See here. This is S-plane. In the S-plane, this is real axis and this is imaginary axis. Okay. Now if the roots of the characteristic equation lies on the left half of the S-plane. What is the left half of S-plane? This is your left half of S-plane. So if all your roots of the characteristic equation lies in the left half of the S-plane like this, then the system is said to be stable system. Okay, then what is unstable? Unstable system, if all the roots of the characteristic equation lie on the right half of the S-plane, then the system is said to be unstable. Okay. Right means if the roots lies in this region, then the system is said to be unstable system. What is marginally stable? Marginally stable system, if roots lie on imaginary axis of S-plane, then the system is said to be marginally stable. S-plane, real axis and imaginary axis. If the roots lies on the imaginary axis, that system is said to be marginally stable. Okay, so this is about different stability concepts of your control system. Okay then. So now already we derived the characteristic equation. This is our characteristic equation. Now we have to find the roots, and then by verifying the location of the roots, we can say it's a stability, and by explaining that stability, in that process you can find the value of k. Fine, but see this characteristic equation. Now if we see the characteristic equation, it is a third order polynomial, means it consists of s cube term. Finding the roots of the third order characteristic equation is very difficult if you follow the basic procedures. For that, we had a criteria called RH criteria or Routh-Hurwitz criteria. According to Routh-Hurwitz criteria, we have to form the process of RH criteria. Okay, in this Routh-Hurwitz criteria, first we have to form a table. S cube, S square, S power 1, S power 0 in this column. Okay, as the equation is, what is our equation? I'll write the equation is our characteristic equation. Okay, so as it consists of S cube, S square, S and some constant, write this, start from S cube. Now you have to fill these rows. First S cube, the multiplication is with 1. The magnitude of S cube is 1. Then you have to write S magnitude, that is 16 plus K. Then here you have to write the S square here. Then here you have to write the constant. Like this you have to fill the Routh-Hurwitz table. Then to get this, simply you do like this. First you do it, then you do it and make divided by 10. So it is, this term is 10 of 16 plus k minus 11k divided by 10. Okay, then for this just multiply this term with 10 and this one with this term. As you have no terms, you can now multiply these two, this one and this one, divided by this. So this into this minus 0 divided by this, you'll get 11k here. You'll get 11k here. Okay, now for marginal stability. The question is, the value of k for which the system is marginally stable. For marginal stability, entire row of the element is 0. One row must be 0. See here, this first row is not possible and second row not possible. See here, third row, 1 0 is already there. 1 0 is already here. So now if it is 0, the system is said to be marginally stable. For that, you have to make this term or element equal to 0. Okay. So it implies 10 of 16 plus k minus 11k divided by 10 is equal to 0. (160) plus 10k minus 11k is equal to 0 implies 160 minus k is equal to 0 implies k is equal to 160. If you keep this k is equal to 160 here, then you're going to get this term is also 0. So you're going to get totally row of 0, row of all zeros means the system is marginally stable. Means in that marginally stable system, I already explained, the roots lies on the imaginary axis. Thank you for watching this video. If you like this video, please don't forget to like, share and subscribe.